Hi, this is the third talk in the fall edition or the winter edition of the seminar series. Looks like we're all stuck in like March 2020. Uh, yeah, really excited to have Professor Sylvia Herbert from UCSD here with us. And she did her PhD with Claire Tomlin's group at UC Berkeley, and she's got a ton of fellowships, NSF, from UC Berkeley and so on. But the one thing that's really unique is this is probably the first speaker we have in our series on safety in robotics and robot learning in general. So we're hoping to have more speakers on this topic going forward. And also, yes, Sylvia's just been talking through all of her adventures about starting off a faculty position in the pandemic. And looking forward to hear from her. Her talk's titled Safe Real World Autonomy in Uncertain and Unstructured Environments.
Okay, great. Thank you so much, Krishna, for that great introduction. Yeah, so this is my talk, and the motivation for my talk is fairly straightforward. It is that we want our autonomous systems to operate safely in real-world environments. And traditionally, coming from the control theory perspective, the way that we've handled this is that we wanted to guarantee the safety of every possible trajectory of our system over time. And now this is great and has led to some really beautiful frameworks, but as we get to more and more complicated systems operating in more unstructured and uncertain environments, especially ones that involve other agents that are uncertain, such as humans, it becomes completely intractable to try to guarantee the safety of every possible trajectory of the system. And because of this, companies have kind of given up on the control theory side of things and instead use a lot of kind of heuristic measures for trying to approximate safety. And this sometimes ends in disaster. So we have, a couple of examples here. Driver says Tesla car gets confused and crashes on highway. And time to panic, a robot killed a factory worker. So I think that there's a need and an interest of thinking about how we can take some of these ideas on safety guarantees and try to make them more applicable to some of these more complicated real-world scenarios. So given that, my kind of central goal is safe, scalable, and adaptive autonomy. And I've kind of approached this goal from a few different perspectives, from the control theory perspective, cognitive science, and learning. And I worked on a few projects kind of spanning this space. I don't have time to talk about all these different projects. So today I'd like to kind of emphasize three main thrusts of my work. The first is just on safety analysis. So how do we ensure that we make guarantees about safety for these systems? And can we make these more tractable? So I've worked on methods for improving the scalability that can allow us to do safety kind of orders of magnitude faster than we were able to before, allowing us to kind of finally compute safety for some more realistic systems. Next, we'll talk about safe decision-making in real time using this algorithm called fast track, or fast and safe tracking. And this is trying to actually make our system able to make real-time, very quick decisions using tools like rapidly exploring random trees, RRT, A-star, et cetera, while maintaining safety with respect to their high-dimensional system. And then finally, I'll talk about safety in human-centered robotics. So when we're actually trying to operate in a world where the environment is uncertain and we have, for example, humans navigating in this, can we try to still reason about safety in a probabilistic way so that we can try to work with these humans? Okay, so given that, I'm going to start by introducing the safety analysis. And here, first, I'm going to talk about the standard approach for safety analysis that we've used, which is Hamilton-Jacobi reachability analysis. And then I'll go into my work on system decomposition and warm start reachability analysis. So this standard approach that we often use, Hamilton-Jacobi reachability, assumes a couple of things. First, that we have a dynamical system where the state of the system evolves over time according to its state, some input to the system that we call the control, and potentially some disturbance to the system. You can think of this as uncertainty in your system or environment, or an actual other player that's working against you. And we also have some sort of goal and or unsafe area in the state space. This is a goal that we might want to reach, or an area that we might want to avoid, or perhaps both. And we want to compute what's called the reachable set. This is the set of states from which I am guaranteed to be able to reach my goal, even in the worst case situation. Even if the disturbance, the wind is blowing against me, I know that I'm guaranteed to be able to reach my goal. And moreover, I have the control policy in order to achieve that. So to compute this, we go through a few steps. First, we lift this to higher dimensional space and we define a cost function over this. So this cost function that I'm drawing here is just simply a signed distance function. It's just saying that we have negative cost when we're inside of the goal. So negative cost is good, and positive cost outside of the goal. And so we simply define this cost function in that way, such that it's negative when we're inside of the goal. We're then going to define our value function over the state, space, and time. So we're going to say that we want this value function to tell us the minimum cost of trajectories of the system starting from state z and time t. So I want the minimum cost because I want to capture the most negative that this system ever achieves, which will correspond to being at a negative cost inside of the goal. So here I'm writing my minimum cost of trajectories over time. So this is as opposed to thinking about, let's say, expected reward or average reward or sum of rewards. Here we care about the minimum that we ever achieve. Here I'm adding in my trajectory notation here. And there's one more step to my value function. I don't necessarily care about the minimum cost of every possible trajectory. I really only need to keep track of the minimum cost of the optimal trajectories of the system. And so for this, I throw in an imp soup, where here I'm assuming that my control is trying to minimize this cost. It's trying to essentially do gradient descent here. And the disturbance is doing the opposite. So I have this imp soup over my inputs, this minimization over time of the cost of my system. So if a point, an initial state and time has negative value, that corresponds to it being able to achieve negative cost over the time horizon. So that means if it has negative value, it's able to get inside of the goal over the time horizon. So in order to actually compute this, it's not necessarily straightforward. It's not always convex. We could have nonlinear dynamics and et cetera. And so kind of the most brute force way to compute this is using Bellman's equation. So here we use the Hamilton-Jacobi-Isaacs partial differential equation, which is the continuous version of the discrete time Bellman's equation. So here we say that the change in my value over time at a particular state is doing a min-max of the gradient. So my control is going to try to do gradient descent along this value function, but it's confined to obey its system dynamics. It has to obey physics. I can't necessarily, if I'm trying my car to move directly to the right, I can't just do gradient descent to the right instantaneously. I need to be able to apply my control that will propagate my dynamics in that direction. And so we look at the inner product between the two. So this term is called the Hamiltonian. So this takes care of my min u and max d, but it doesn't take care of this minimization over time. And so we add one more minimization here that encompasses the minimization over time effect. Okay, I know that was a lot of math early on, right out of the gate, but let's see what this actually does when we apply this update equation to our system backwards in time and do dynamic programming. So this is my value function. I'm starting at that goal and working backwards in time and computing the value at each of those time steps. So here, let's say that I care about my value stopping at a time step of 10. Now, everywhere where the value is negative, that corresponds again to a trajectory that is able to achieve negative cost over time. So therefore, if I slice this at 0 and flip it back around, everywhere where that value function is negative is within my reachable set. It contains the set of states from which I am guaranteed to reach my goal while dealing with worst case disturbances. If instead this is an obstacle, we can compute the opposite. This is the set for which we will, no matter how hard you try to avoid the obstacle, you will end up crashing into it. So this is nice because traditional Hamilton-Jacobi reachability analysis provides safety guarantees and control policies. The gradients of this value function inform us of the direction that we need to apply our control. And we have lots of different tools now for actually using this in kind of a user-friendly way, from MATLAB, Python, C++, interactions with ROS, et cetera. So it's fairly user-friendly. But this technique struggles a lot with complex models and uncertain environments. So let me explain what that means. So with complex models, the challenge here is that we're gridding up that state space and then computing this PDE at every single point in that state space. So when I add more and more states to my system, as it gets more and more complicated, I'm adding exponentially more grid points that I have to reason over. And very quickly, this becomes completely intractable. And so in practice, instead of using full system dynamics, we often use really simplistic models of our systems and do safety analysis with respect to them. So we might, for example, model a human as simply a double inverted pendulum, which does not capture all of the aspects of a human. And therefore, a safety analysis with respect to this might not actually hold that much weight in the real world. The other challenge is with uncertain environments. So there are some aspects in which this is really nice for uncertainty. So I mentioned that we can have disturbances in our system where this can be uncertainties in our model or how our system interacts with the environment. But we need to know what the bounds are of that ahead of time. What will be the worst thing that the disturbance can do to us if we're doing a worst case analysis. We can also handle potentially goals and obstacles and even moving obstacles. So here I'm showing an obstacle in red and a second cost function where the cost now is high inside of the obstacle and low outside of the obstacle. And if I know exactly how that's going to move over time, I can actually incorporate that into my computation. So this is one of my favorite videos because I think it's so beautiful how as the obstacle is moving through time, it slices through our value function computation. And so when I then flip this back over, I'm given what's called the reach avoid set. The set of states from which I'm guaranteed to be able to reach my goal without running into the obstacle first. However, this required me knowing exactly how that obstacle was going to move so I could pre-compute this value function. And so when you're dealing with the real world where you don't necessarily know how this will happen, this does not work. So given that, I've worked on some techniques to try to scale up our efficiency of computing this so that we can deal with more complex models and we can update those analyses as we learn more about the environment. So one is on system decomposition and the other is on warm start reachability analysis. So the system decomposition idea is fairly simple. Let's say I'm going to use as my toy example this four-dimensional Dubin's car, where my position is a function of the speed and the cosine of theta, as well as the speed and the sine of theta. My change in my angle is my rotational velocity, and my change in my speed is my acceleration. Let's assume I have control over these two. Now we can handle this system, but as a toy example, what would happen if we wanted to break this down? Well, okay, so x depends on theta and v. Y also depends on theta and v, and those each depend on their inputs. So this is a coupled system. There's no clear way of how we'd be able to break this up and look at each component separately. So we asked, well, what if we just forcibly ripped this apart? Just split them apart like this. And now we have missing information on each side, right? We don't know what v is over here, and we don't know what theta is over here. We're going to replace that missing information with the worst case assumption over what it could be. So treating this missing information as a disturbance to the system. We then have a 2D system over here and a 2D system over here. And we'll combine them by saying the value at a particular x, y, theta, and v will be the max or worst case value of the two together. So this is kind of what it looks like in a cartoon form. If I have my four-dimensional space and I look at the x theta subspace and the y v subspace, I'm going to take my goal and project it down onto each. I'll then compute my value function in the 2D space and lift it back up. The same thing over here. And then take the max, which in this case is an intersection between them, which will look like this. Now this is guaranteed to give us a conservative under approximation of the true reachable set. So here's an example for that. Here I'm showing the x theta y subspace and the x y v subspace. In green, I'm showing the full formulation reachable set, and in the purplish, I'm showing the decoupled approximation. And we don't get all the volume back. Here we're only getting 20% of the volume, but we do that in 86 seconds compared to the 12 hours that it would have taken otherwise. And this smaller volume is guaranteed to contain states from which I'm able to reach my goal despite the disturbances.
Can I ask a question?
Oh, please.
So I just don't quite understand how you're getting the bounds on the like things that you took apart. And obviously it would seem like how tight this thing is going to be is going to depend a lot on how.
Absolutely. Yes, that's a really good question. I don't usually get that question. So sometimes it's very clear. So for example, in one of these things I made like theta a disturbance. And so you know that theta will be between minus pi and pi. And other times, like the velocity being a disturbance, you need to have some notion of kind of the max velocity that the system can output. And so you do need to have some user-defined knowledge of that disturbance bound. There is, so I have a student that has been looking at a way of like iteratively, as you're computing this, learning the bound and being able to incorporate that back in, but we haven't published on that yet. Another thing is sometimes this can be extremely conservative. So if you give theta as your disturbance and you allow this disturbance to flip around your car any way that it wants as you're trying to compute this, then it can be, you won't be able to move at all because anywhere you try to move, your disturbance will just flip you in the opposite direction. So in the paper, we also talk about methods of being able to break that down so that you can reduce conservativeness. But it's beyond the scope of this talk, but I would love to talk more about that offline if you're interested.
Cool, thanks.
Okay, so we also have this other technique, warm start analysis, and this was really motivated by looking at the tools in reinforcement learning that use discount factors and whatnot to be able to initialize with a guess and be able to iterate that guess towards the correct solution. Because we might have changes in the autonomous system, our model might not be correct anymore. We may have changes in our external disturbances. We may have changes in the behavior of other agents in ways that we didn't expect. Here, this is one of my favorite videos of some children terrorizing a mall robot that had to learn to stay near parents so that the children wouldn't get to it. So in general, we'd like to be able to update our analysis. And we found by kind of using this warm start framework that without a discount factor, we can guarantee that if we start with an overly optimistic value function, so one that assumes that the world is great, and it turns out that the world is not as good, we can update this and actually be able to achieve the same exact convergence. If instead we find out that the world is less bad than we expected and we had an overly conservative value function, well, then we're guaranteed to converge to a value function that is not more conservative. It can only get better, but it might not reach the true optimistic value function. So this is nice, but the main point in trying to do this is that it really speeds up our computation. If we can start with something that is very close to what is the true value function, then we can very quickly update it over time rather than starting from scratch. And this is really useful online because as you find out that something is different than you expect, it might be more efficient to just update that area rather than redoing everything from scratch. So we have a couple projects on this. Here's one that we submitted to ICRA that was just in simulation because of COVID, where we have this quadcopter that's responding to changes in wind gusts and updating its safety analysis online based on this. And we're hoping we have a group that wants to apply this to quadcopters doing radiation detection at the Oakland shipping port and dealing with wind gusts there, which will be fun. But the computation is much, much faster doing these methods. So doing just decomposition, this is what we have, and then doing the decomposition plus warm starting, we end up being able to update much, much, much faster. This has also been used by some of my colleagues. So here's a project with Andrea Baichi and Somel Bonsal, where Somel had this neural network-based controller that inputted the perception of the scene and outputted waypoints that he wanted to go to, and then used splines in order to go to those waypoints. But he didn't have any safety guarantees on this. So they implemented a local version of this update, where as they discover more and more about the environment, they can actually update their safety bound here, as you see it moving over time. And then use the override safety controller whenever the neural network-based controller was violating the safety conditions. And they found that using the local warm starting update, they were able to achieve much faster convergence on updating their safety analysis as they learn more about the environment. So these are some theory and tools for scalability that makes the safety analysis more tractable. You know, using this, we've been able to take systems where we couldn't do safety analysis to, and now do it on the order of like, you know, a few seconds to minutes, but it's still not quite at the point of doing kind of real-time analysis for something that's moving as quickly as, say, a quadcopter. So this kind of motivates the second part of my talk, the safe decision-making in real time. We really need to make decisions quickly in real time, and we'd love for those to be safe. So if we can't update our safety analysis quickly enough, how do we go about doing this?
I have a quick question, Sylvia.
Sure.
So do you have any comments on the scalability of the system as your, let's say, dimensions of the state space or degrees of freedom increase?
Yeah, that's a good question. Kind of like a rule of thumb type of analysis.
Yeah.
So if you're just doing the like vanilla reachability without any of these other techniques, and you're gridding up your state space uniformly and doing that, our C++ implementation can handle like 6-dimensional nonlinear type of things. But even that is like, it takes a while to do that. If you do these decompositions, adaptive gridding, warm starting, it really depends on the structure of the system and the structure of the problem, how quickly it will converge. So you can imagine if just a very small area of the state space is changing, it will converge very quickly. If a lot of things are changing, it won't. So it's hard to give a hard and fast rule there. One of the most exciting things that I'm really looking forward to using is that colleague of mine, Somal Bansal, who's currently at Waymo and then starting at USC, recently submitted to ICRA this algorithm called Deep Reach, where he's using sinusoidal neural networks in order to approximate these value functions and getting really impressive results with scalability. And it scales in a very different way than the scalability that here. And I'd be happy to talk more about that method or other approaches to try to do this. There's also a lot of approaches that do linearizing or do bounding things with polytopes, or if you are learning your policy offline and then just plugging that into your system, and then you want to know the reachable set based on that, there's techniques for that to go back and forth between the policy learning and the value computation. So yeah, there's a lot to talk about on that, and I'd be happy to talk more afterwards. But that's the gist.
Sort of follow-up I had on that was, do you think do we absolutely need to grid up everything and evaluate value functions there, or can we be smart about sampling where we evaluate our value functions?
No, we should absolutely be smart about sampling where we're doing this stuff. I mean, this is something that the fluids community has known for so long, that there are areas of the dynamics where it's really important to capture everything that's happening there, and there may be areas in which it's a lot less turbulent and you can kind of approximate it pretty easily. In the lab that I was in Claire Tomlin's lab, we hadn't really gone to doing adaptive gridding just because people were excited about other research problems, but adaptive gridding should absolutely be used, and like sampling intelligently and all of that. And I think that would really scale up this computation, but we just haven't had someone who wants to do that. So if anyone here wants to do that, let me know. Okay, so fast and safe tracking. So I've talked all about this like slow and accurate planning. If you give me a goal, give me an obstacle, I can eventually tell you the optimal control for getting to that goal. On the other extreme, we could have fast but less accurate planning using something like rapidly exploring random trees or A*, where we're just very quickly finding waypoints, connecting them, and getting to the goal, for example. Now this is great because it's very efficient, but it may not be dynamically feasible, and it may not be robust to disturbances. So you may find when you actually try to follow this, you can't follow it exactly. So how do we deal with the balance between these two? Well, in trying to learn about this, I came across a lot of work trying to explore, like, how do humans plan in real time? We are very complicated high-dimensional systems, and we have limited compute, and yet we seem to manage most of the time to plan in real time. And there's a research in cognitive science that suggests that humans plan using very simplistic models, but with an understanding of the uncertainty around that and how it maps back to their high dimensional system. So when you're, pouring your coffee, you're not using, the low level plan for how to do that. You have a high level model of how to do this, and then you are able to track that very efficiently using your full dynamical system. So we were wondering if we could do the same thing. Can we, have our system think of itself as a very simplistic model, plan with that, but with an understanding of the uncertainty, the bound around that maps back to the high dimensional system. So in other words, we'd like to plan online using that very simple method, but with a bound around this that tells us, the maximum deviation that we will have as we try to, enact this plan. So here's an example of what we're trying to do. We have this, I think this is 7-dimensional plane that wants to plan around these buildings that pop up in real time. And we want to have some bound around this. Important things to keep in note. We don't know the environment ahead of time here. We're using the low-level planner to come up with a plan as it's learning about the environment. And therefore, we don't know what that low-level planner is going to do ahead of time. We don't have a nominal trajectory here. So how do we deal with this? So I'm showing kind of my two identities of my system. One that's the full high dimensional system and one that is its smaller planning model. And I'm going to call these the tracking agent and the planning agent. We're here, I'm going to make my tracking system model this 3D Dubin's car. Normally it would be something much higher dimensional, but just since we can see in 3D and I want to show some graphics, let's stick with 3D. And then the planning system model here, I'll just make it a 2D system that directly controls its velocity. So let's think about the behavior of these two. I know that my tracking agent is going to try to track or pursue my planning agent. So I'm going to call it the pursuer. My planning agent, I don't know what it's going to do ahead of time. I don't have that information. I don't know what the environment is. I might not even know what the algorithm is. And so again, we're going to replace that missing information with a worst case assumption. So saying, let's assume that the planning agent is being as difficult as possible to follow. Will we still be able to follow it? So we're going to actually treat this planning agent as an invader and look at the pursuit evasion game between these two identities of our system. So we're going to ask, given this setup, what will be the largest relative distance over time between the two agents? We're note here that the largest relative distance will be the worst possible tracking error over time, which will be our tracking error bound. So since we care about relative distance, we care about relative state. And since we care about relative state, we care about relative dynamics. So first I need to determine what are my relative dynamics between these two systems. To do this, I'm going to set my planning agent at the origin and look at the dynamics of my tracking agent relative to that planning agent. In this case, it's as simple as taking the Dubin's car dynamics and subtracting out the planning agent dynamics. Once I have my relative dynamics, I've defined that, my next step is to define my cost function. So my cost function here, I'm going to say, is distance to the origin. Recall the origin is where the planning system is. So this is relative distance to the planning agent. And now I'm going to try to capture the maximum cost of optimal trajectories over time. So the maximum cost in this case is the maximum relative distance that will ever occur over time. So here I have my value function again, where now I'm going to take the max over time of L of my trajectories. And here I'll go ahead and put in my trajectory notation. The tracking agent is going to try to minimize this cost and try to reduce the relative distance, whereas the planning agent is trying to maximize the relative cost in this worst case analysis. So we go ahead and put in our int soup, and then we evolve this over time based on those reachability equations that I showed you before. So this is what happens when I propagate this backwards in time. So this didn't mean anything to me. I didn't understand what I was looking at. So if you're like me, let's go down and break this down and figure out what exactly is happening under the hood here. So here I'm showing slices of this value function. Those slices are seen over here in 2D, and they're seen over here in their full 3D. So the slices look like cylinders because I care about the cost in X and Y, and the cost is constant across theta. I don't really care what the relative heading is in this particular case, though you could if you did. Down here, I'm showing the slice at theta equals 0, which means that the plane is pointed to the right. So if I look at these slices, you can think of them as candidate tracking error bounds, and I want to know if they will be valid. So given that I know that in this case, my plane is pointed to the right and has this kind of fixed radius of curvature, and I know where my planning agent is, it's always at the origin, what are the set of states I can start in such that I can stay inside of each of these bounds? Well, over here, if I start here, I'm going to have to leave this bound in order to come back in. So this is not an okay initial state for my system to be in. I would have to kind of push this back such that I'm just able to stay within this bound relative to the planning agent. If I start down here, well, that's fine. I can turn right inside. And if I start over here, well, that's fine. I can go right into the bound. So I'd expect it to look something like this, the set of states I can start in such that I stay inside of this bound. As I choose smaller and smaller slices, you would imagine that I need to get tighter and tighter initial states until eventually we get to a point where even if I start back here, I'm going to have to leave the bound in order to come back in. So given that intuition, let's go ahead and propagate this value function again and see how it matches. So you see that we pull away from the right side as we expected. And over time, we get to the point where this slice is no longer feasible. I'm going to keep running this to convergence. And eventually it stops and it converges at this point. So here I have multiple slices I could take that each have valid bounds. If I start inside of this purple slice, I'm guaranteed to stay in this bound. If I start inside of this red slice, I'm guaranteed to stay in this bound. In fact, since it's converged, I can say something stronger. If I start inside of the red, I'm guaranteed to stay inside of the red slice. And here's what they look like in 3D. You can think of this as like stacking and rotating this across the theta dimension. Okay, so we computed our converged value function. We're going to take the value of the smallest invariant level set. We're going to try to take the smallest slice here and look at the bound there. And this is because we typically care about minimizing error. So I want to choose the tightest error bound possible. Now this is my tracking error bound in 3D, in X, Y, and theta. But my planning algorithm is only aware of X and Y. And so I'm going to go ahead and project this down onto the XY space. And this is what my error bound looks like for the planning algorithm. Intuitively, this means that if the planning algorithm, if the agent's at the center, the tightest bound I can stay with, and with respect to it, is one in which I'm doing donuts around it, turning as hard as I can to the left or the right. Apparently, this is how wolves chase their prey. So we have our tracking system model and our planning system model. From this, we got our relative dynamics. And from that, we got our tracking error bound that we'll use for our online planning algorithm, and our tracking controller that we'll use for our online control. So this is what it looks like online. I start by figuring out where I am, where the tracking system is, and use this to initiate where I want my planning system to start. So where I want to start my plan. I'll go ahead and put that state into my path or trajectory planner, whether it's model predictive control, A*, what have you. You're also going to put into this planner the environment. You're going to sense obstacles, and then you're going to augment them by the tracking error bound. So it'll look something like this. Then this path or trajectory planner will output wherever it wants to go next, based on however it does that. And then you just have to look at the relative state between where you are and where this plan is. And based on that relative state, input that into your value function to find the gradient that tells you the optimal control to chase the state and pursue it. And you may not be able to track it exactly, but you know that the delta that you'll have here will never be more than this error bound. And so you may violate the augmented obstacles, but you won't violate the true obstacles. And then you just repeat this. The important things to note here is that we're really just doing this very kind of light wrapper around your path or trajectory planner, where all we're doing is augmenting obstacles, which we typically do in robotics anyway, but this is by this kind of rigorously computed bound. And then we're just using basically a lookup table to look at what the tracking controller is based on the relative state. So we offload all of the dealing with the environment, all the planning to the planning algorithm, and we just take care of the safety offline. So this is what it looked like for our very first simulation when we were trying this out. Here we have this 10D mirror hover quadricopter model where we want to try to get it to this goal, and there are unseen obstacles in this space. Even if we could see the obstacles, the time it would take to do the full reachability analysis on this using the standard methods would have been like years. I think it would be a lot faster now with this deep reach algorithm. but it would not be tractable at all historically. Even doing the pre-computation, we're going to plan using this, and doing the pre-computation of the relative dynamics here will be challenging, but we're going to do our decomposition work to split this into the X, Y, and Z dimensions. We'll then pre-compute our 10-dimensional tracking error bound, shove that down onto the 3D space for the planner, and that's what it looks like here, this box around the planner. So here now I'm planning using RRT, that's what my green star is. As it senses obstacles, the obstacles turn red and it replans. And then I'm chasing this plan using my 10-dimensional quadcopter. And so we're actually doing this online. And you'll note that even when the RRT does something unexpected, like this really sharp turn that it does here, we're able to stay within that bound because we accounted for worst case planner behavior. So because we're having no kind of communication between the tracker and the planner, we have to account for worst case possible behavior of the planner. Here's what it looks like in some of the experiments. So here's a project from Professor Shankar Shastri's lab where they're doing this like VR thing of having quadcopters go through hoops and stuff, and they're using Fast Track as the underlying controller for that. Here's a project with Marco Pavone's lab at Stanford in which we used sum of squares optimization instead of reachability in order to compute that bound. And then here's a project from Professor Claire Tomlin's lab in which they were doing this classification-based approach to computing the policy between the tracker and the planner offline using neural networks to be able to scale this up more. This has also been used in various other labs and universities at this point. I think the reason why it's been used is because it's a very lightweight wrapper. So it allows us to just kind of robustify fast and simple planning algorithms without any need for sophisticated communication between the planning side of things and the safety side of things. So it just you just kind of throw it on to whatever planning algorithm that you would like to use in a standard method. So that's nice. Oh, go ahead.
Yeah, so I'm not 100% sure I understand it completely, but are you paying some kind of price here in terms of performance? And I guess what I'm thinking about is like, is this like kind of myopic in terms of always looking at the next waypoint only, whereas some other planning algorithm might be able to more cleverly like smooth out the path between waypoints, something like pure pursuit or whatever would like consider the entire reference trajectory rather than just chasing the next waypoint?
Yeah, absolutely. Okay, so those are really great questions. So yes, this is just looking at relative state, so like instantaneous state for safety. And if instead you're looking at something like looking at the nominal trajectory, the whole trajectory over time, and then computing the safety with respect to that, then you can improve the performance by quite a bit. Because if you know how the planner is going to move beyond just right now, you can incorporate that into your worst case analysis. And so this is actually kind of similar to some work by Professor Aniruddha Majumdar at Princeton, where he does these safety funnels, where instead of thinking of a safe bound around an instantaneous point, now that he has a library of possible trajectories you could take, and kind of given each trajectory, what is the safety funnel around that? And then online is just a matter of kind of like slapping together the nominal trajectories quickly enough so that you can plan efficiently. So there's in general, there's this trade-off between assuming no information about what the planner needs to do at all, and having potentially really conservative bounds, which is what I'm about to talk about, versus requiring more from the planning side of things to give you more information to you and maybe having more restrictions on how you use that online, but being able to make kind of better, tighter assumptions about what the safety will be there. And what I'm about to talk about now is kind of trying to meet at the middle between those two extremes of having just a library of trajectories versus doing an instantaneous single model. And the issue is, great segue, the issue is this can be like really conservative. So I'm assuming worst case planning behavior at all times, assuming that the planning agent is actively working against me, then clearly I'm going to take some very conservative routes. So for example, here, probably I could have squeezed between these two obstacles to get to the goal. But if I'm assuming that the planning agent might like do a quick 180 to try to mess with me and I'll end up crashing into the obstacle, then that's not considered safe. So I mark that as unsafe. But in reality, it's probably fine. So I was trying to deal with this, and at the same time I was reading this book, Thinking Fast and Slow by Daniel Kahneman. He's the Nobel Prize winner in economics and is a famous psychologist. And he has this framework where he asserts that humans have a fast mode of thinking and a slow mode of thinking, where our fast mode is our kind of automatic mode that is continuous and error prone, but very effortless. And we can switch into our slow mode that we use only when we need to. And it kind of like takes effort and brain power, but is a bit more reliable. And there's this question of how do you intelligently switch between these two modes of thinking? And I was interested in maybe trying to apply this to this framework. So if I have my same high dimensional model, what if instead of just one planning model, I had kind of a suite of them? So in the simplest case, let's assume it's literally the exact same as before, but they're actually moving at two different speeds. So in one case, I allowed the system to move quickly. In the other case, I forced the planning algorithm to move more slowly. This would essentially mean in one case, you're using someone like me to plan the path through the environment, and I am very slow. And so you'll have a tight error bound because it's easy to keep up with me, but you'll move through the space very slowly. Whereas if instead you're planning with like Usain Bolt, you move super fast through the space, but it'll be really hard to keep up with him. So you'll have a larger error bound. So can we adaptively choose when to switch between these modes? You know, here now we have a suite of error bounds that we could choose between. And when we sample a point that's in collision using the fast mode, we could say, if I'm able to communicate to my planning algorithm, hey, would you be willing to switch into the slower mode? Would I be able to treat that as a safe space? And can you then stack together switching between these two different modes? So that will let you kind of quickly go through here and then slow down to kind of squeeze between these two obstacles. Note that switching safely is also non-trivial. We had to do some other reachability stuff for pre-computing that. But given that, we have a proof of guaranteed safety throughout this process. So we have now we've talked about this suite of going from assuming the planner will do absolutely anything at any time, to assuming that we only let the planner choose kind of a very restrictive set of trajectories online, to now something in between of saying you're kind of restricting the trajectory space that the planner can choose between online. So, it's interesting trade-off throughout that space. So this was fun. So here's an example of that same simulation where here we're using this big error bound to move very quickly through the space. When it samples that it's in collision, it adaptively chooses to switch into these slower, tighter error bounds kind of on its own using this hybrid framework. And then when it senses that it has more space again, it then goes back into kind of the fastest mode that it can, given the clutteredness of the environment. And then here's an example of it in hardware. Here we hung these lanterns in the lab, and then we had the system switching into a tighter mode when it sensed that it needed to squeeze between these obstacles. Okay, I know I'm running a little late on time, so I'm going to try to get through. I think this is a fun section, so I'm going to try to get through it, and then maybe I'll skip the future work stuff for now, but we can chat more offline if people are interested. Okay, so safety in human-centered systems. So I talked about, if I am a robot and I'm trying to get to a goal and I have some obstacle here, this human, if I know exactly how that human is going to move over time, great. I can just incorporate that into my computation with that beautiful video that I showed you before and have my reach avoid set. Problem is, humans don't usually tell me exactly how they're going to move over time. And so historically, in my field, we've done a worst case analysis of this. We've said, the human might go anywhere at any time, and you need to avoid anywhere that they could possibly be. So this means that we treat the obstacle as a growing obstacle like this, and we incorporate that into our analysis. The problem is, if you assume that all humans are out to get you, you end up having very, very small spaces from which you think that you are safe. So how do we deal with these two extremes and trying to blend the approaches together? Again, we turned to cognitive science and we asked, how do humans deal with other humans? They clearly have to do this on the sidewalk and stuff, so what do we do? And there's a lot of research that suggests that, perhaps we can model humans as, again, having simple models and kind of compute probabilistically where they might go over time. And we can do this using things like the noisily rational Boltzmann model, where here we're computing the probability of a given action of the human based on their current state, this theta term, which defines the learned human objectives, what humans tend to want to do, and this beta term that controls the variance of our distribution. So doing this, we can assume, generate this based on assuming that humans are exponentially more likely to take actions that lead them towards their goals, and then propagate this through the dynamics in order to come up with a probabilistic prediction of where they might go. So we went ahead and incorporated this. This is our kind of experimental platform. Here's me. I'm wearing this shirt called a human being, so you can identify me. Here I am in the Ross visualization, and you see the prediction coming out of me. And then you'll see the quadcopter flying across. Here it is, and here's its plan using fast track of where it wants to go to its goal. Here, I go straight to my modeled human goal. The robot goes straight to its goal. Everyone behaves rationally according to how we expect humans to behave, and it's all fine. So assuming that humans behave exactly the way that we want them to, we can go ahead and use this. Problem is, humans often don't behave by going to straight lines towards their goals. And so what happens if our model is incorrect? So here we have this coffee spill on the ground that the human is aware of, but the robot isn't. So the robot thinks that the rational thing for me to do is to go straight to my goal. If instead I move around this unmodeled obstacle, well, we see that it kind of responds somewhat, but it doesn't give me enough clearance because it does not expect me to continue moving away from the goal. And we end up in this collision. So how do we avoid situations like this? Well, we asserted that when we are dealing with other humans walking down the sidewalk, we have some prediction over what we think the other people will do, but we can adapt this prediction when people aren't matching what we expect people to normally do on sidewalks. And so we can model this using that beta term that controls that variance, where if the beta is low, then we go back to what's called a full forward reachable set, assuming the human might go anywhere at any time. When beta is high, it does the other extreme of saying, okay, this human's definitely going the way that I expect. And so can we update our distribution of beta over time as we see if the human is matching our model or not? So this is what that looks like with this confidence-aware prediction. So again, we're not trying to come up with a perfect model of a human, we're just getting confused when the human isn't matching what we expect. So here, as I move around the obstacle, you see the distribution spreading out around me. And then I go back towards the goal, it tightens back up. Let's look at that again, and you'll see the robot behavior in response. So it becomes more and more confused and takes a wider berth around me because it's reduced its confidence and therefore increased the variance of where it might go over time. So we can't always find a perfect model, especially of humans, but we can use structure where it exists and revert to cautious predictions where it does not. We found that this is also useful for dealing with multi-agent situations. So if, for example, we have two humans now, and we would like to be able to reason about the fact that they will move around each other and respond to each other. But if one human we're reasoning over, let's say 1,000 states, then 2 is 1,000,000, 3 is 1,000,000,000, and so on and so forth. So again, we deal with this scalability issue. If instead my robot thinks of each human completely independently, humans can walk through each other as they go to their goals. This is clearly not a good model of how humans work. But when the humans don't match that model, my robot will become more confused about what they're doing, increase the variance, take a more cautious approach until they match back up, and then it can continue forward. So on the multi-robot side, we can also plan sequentially using these, and we can plan much more quickly if we do fast track. So we can plan using very simple paths with bounds around those paths and communicate those to each other. So here online, we're going to try doing that. I have 2 quadcopters that are going to move across the space. And then you have me, and then you have my colleague, Professor Jaime Fazak, and we're going to move across and have to move around each other too. First, let's just go ahead and look what's happening in the actual video. So you see the quadcopters take off, and then Jaime and I start moving. Jaime insisted on dancing the whole time because he said that it had to be robust dancing. So you see he's dancing, but we have to kind of move around each other as we get to our goals. So let's see what's going on under the hood there. So here's me, here's Jaime. We're gonna go across to our goals, and then here are the 2 robots. So you see as we start moving, it becomes more confident over what I'm going to do. never becomes confident about Jaime. But you see, it reduces its uncertainty here. But then when we move around each other, you see that the uncertainty grew and it had a more cautious prediction of where we might go. So then, if I go back, you'll see that one of the quadcopters actually has to replan around us based on this.
I have a question.
Yeah, sure.
So in your like recap slide before you talked about the multi-agent stuff, you said that you can exploit structure where it exists.
Mm-hmm.
But I missed exactly how that happens. So is that
sure.
like in the model itself, that's that like probabilistic model over inputs? Because like thinking about how people walk on sidewalks or like how cars drive down roads, like they might be erratic, but still there's like a lot of structure we can impose. And how does that work here?
So the theta term that was in there was the learned human objective. So for the example of the sidewalk, I might assume that humans want to walk in straight lines towards the end of the sidewalk and use that as the theta term in there. And other parameters of what you can change there is the Q value function in general. I mean, we talk about changing the theta, but how you impose that structure of how the humans decide where they want to move cognitively can be played with, as well as the physical dynamics of the human. Here, we're assuming humans are point masses that move in straight lines towards goals, and you can think about changing around what the dynamics of the humans are there. So but actually, general, okay.
Sorry, this is something that in this setup is like pre-specified as part of the model and not learned. Is that right?
Right. So in this particular example, we did that. There's some follow-up work, and this was with Professor Anka Dragan at Berkeley. There's follow-up work on her lab of now can you learn the human objective? So when do you just be confused versus when is this actually information that you need to encode into how you continue to make predictions about humans? And so in general, this has been a hard problem to figure out when should you be confused versus when are you actually learning important information. And they're interested in exploring this and different ways of actually learning this. So yeah, there's a lot of interest in this area, but it's by no means even close to being solved. So if people have ideas, please help us figure it out. Okay, so I have some slides of kind of next directions that I'm interested in, but in the interest of time, I know that I'm running out. I'll go ahead and stop this for now, but I can stick around for a little bit if people want to keep chatting. But given that, let me go ahead and just fast forward to my last slide so people know. Here, sorry. Here is my email address, if anybody wants to follow up on any of this, as well as my website with a little bit more information about each of these research projects. And here are the things that I talked about today. And then here are some of the directions that I'm excited about for next steps. With that, thank you so much. And sorry that I went a little bit over time.
Awesome.
So there's actually a question on the YouTube stream. The hard part is I'm not able to associate when, at what point during the talk this question was asked. I was just so engrossed in the talk. So the question was, are the obstacles assumed to be static? And I'm assuming it's somewhere towards like the second project that you were describing.
Yeah. Okay. So in the fast track algorithm, we assumed initially that the obstacles were static. And the point of that is so that on the planning side of things, we just have a minimum sensing distance. And when you sense the obstacles, you can then augment them by this bound. The interest in doing the human thing was, what if we can't assume that we just have floating lanterns in the room and we have to actually predict where things are going to move. So we actually, with that probabilistic distribution of where the obstacle will go over time, we then look at the integral of how much of that distribution is inside of the tracking error bound. And if it's above some threshold, then we say it's too likely that the human and the robot will be inside the tracking error bound at the same time and reject that point. So that's how we do collision checking with the moving obstacles of humans.
Great. Yeah, it was indeed with respect to fast track.
Cool.
Any other, I mean, I have like a million questions, but any other questions from the?
Looks like there's one in the chat.
I was wondering if these concepts of safety could extend to scenarios where there isn't clear obstacle free space separation. For example, if forests are plenty, there are plenty of obstacles that a vehicle can drive through, like small bushes, and free space where the robot can get stuck like mud. Sadly, we don't have models good enough to know in advance if it is an obstacle for sure.
Absolutely. So that's what one of my future slides is this, what does safety mean in all of these different kinds of contexts? So historically, we've just considered it as like never crash into anything. And you can very clearly define what's considered the failure set, the set in your state space that is not good. But in a lot of these cases, like many of the cases that this person just wrote, it's a lot more complicated than that. And so, yeah, there's a ton of really interesting work right now in the learning safety side of things of what assumptions do you need to make such that you can be able to determine how safe certain actions are. And the more assumptions you make, the easier it is to be able to do this. So for example, if I assume that my level of unsafety changes with a certain Lifshitz constant, that as I get closer and closer to the area that's unsafe, I can sense that more and more. Then you can use something like a Gaussian process to determine when you're getting too close to the unsafe bound. If instead safety is kind of a discontinuous thing where it just will, you're safe, 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 and then all of a sudden you've done something terrible and you can't sense that ahead of time, well, then you have to instead think about like, well, how risk averse do I want to be? How willing am I to explore these different areas? One project that I have in collaboration with Professor Michael Yip at UCSD is asking this for surgical robots. You know, how much can I deform the objects around me until it's considered unsafe? And so, yes, I think that this can be extended to these different scenarios. Some in ways that are more easy than others, depending on the specific situation and the assumptions you make. But in general, I think this is a super interesting open field. A conference that is really exploring these types of questions that's new is called L4DC, Learning for Dynamics and Control. I would definitely recommend checking out some of the YouTube videos from that conference if you're interested in this topic.
Great. Yeah, I have a question that's not really a question. It's more of like trying to get your perspectives on. There's a lot of people doing learning, and learning systems are historically they've been not so interpretable, or you don't actually get safety guarantees out of learning system. So do you have any opinions on where your sort of research trajectory interjects with those black box style learning systems?
Yeah, so one of the areas that I'm really interested in is taking, so some of this work that I've talked about with warm starting and stuff like this, you're able to take an initial guess, so some initial value function that you've computed and be able to then work with that towards the guaranteed safe solutions. And so especially with some of this, I mentioned the deep reach and other methods for doing these more scalable techniques that don't have guarantees associated with them, trying to be able to blend the approaches in the toolboxes so that you can do an iterative thing between them, I think will be really interesting. There's also this whole subfield of people who are treating, and again, L4DC is a good place for this, people who are treating the learning process itself as a dynamic system, and then asking, how do I ensure the safety of this system as I go through the different layers of the neural network or whatnot. And so there's a lot of kind of interesting approaches to trying to make the learning process more interpretable by using the tools from control theory, which is really cool, but way beyond my work.
Thanks.
Yeah, I was sort of, I'm glad you asked that, Krishna. I was sort of thinking along the same lines. I mean, so like in some of this work, it's like there's contexts where it's feasible to model disturbances. And then there's other contexts where it's like, you don't even know, like, you don't even know what the disturbances are. Yeah. Like, you don't know what you don't know, or like your model, you don't know if your model is like out of distribution or that you're getting. Yeah. And now like each extra layer of that cake that you put on is like an extra, I don't know. So like at some point, like, I guess the hard thing is that to have safety guarantees, somehow with each extra degree of uncertainty, you just add another layer of conservativeness, and then you end up with the like freezing robot problem where your robot just, the only safe thing is to just like sit there and do nothing forever for the rest of time.
Yeah, yeah. If you can't model anything, then in order to make a full-on safety guarantee, you have to be able to like test every possible scenario. And so you lose a lot of edge cases and stuff in general when you're thinking about autonomous driving and stuff like that, when you're just sampling different situations. But on the other extreme, you can't model all these situations and be able to do verification from the theory side of things. And so there's a lot of interesting stuff in between of trying to like think probabilistically about how safe you're going to be when you take different actions. And so there's some really cool work thinking about in a more stochastic sense, safety, as well as thinking about if you have, like I was mentioning, a limited budget of failures, you're allowed to fail a certain number of times because you can't know everything about the space, but you want to adapt how you behave as you fail so that you fail less and less and become more conservative over time. How do you incorporate that into your algorithm? But yeah, it's a super hard question, and I think a lot of people are trying to figure it out.
Yeah.
I don't have the answers.
I really like this last line of work that you discussed, because I mean, like somehow when I project it onto like the way that we do things, like the way I drive a car or whatever, so much about my like model of what other people are going to do is informed by how much they're adhering to like what my prior expectations of them are, right? And it's like,
absolutely.
As soon as they start to deviate from what seems like what I was expecting, then my uncertainty over their future actions goes up a lot, and I start to behave a lot more conservatively. And somehow humans are able to reason about those things like at a fairly high level of abstraction and extremely efficiently. And so
I try. I pay attention to this a lot when I'm driving. When someone does a slight thing, like a slight swerve or something, and my hackles go up, like, do I have a model in my head for how a drunk person drives? And am I like predicting for that? Or am I just being like, I don't know where they're going to go. I don't know what they're going to do. I just need to like get into the far lane. And I'm trying to get a sense of like, how much do I have different models for humans versus how much do I have just like some very simple set of models where I just reason how confused I am. One both nice and frustrating follow-on project to that is that we actually tried to, I think I maybe mentioned this before the talk, we tried to incorporate switching between different levels of sophistication in our models. So switching between when do I have to know that humans move around each other and use something more sophisticated there for planning and predicting what they will do, versus when can I just treat them as totally independent and unaware of the world. And we found that in this particular setup where you just have a quadcopter trying to move through the space with the human, every time just the like dumb, simple, generate super fast predictions and just get confused, outperformed both in terms of efficiency and safety, actually trying to like adaptively switch between your model of the human online, because that would just take so much longer. I do think that there will be some scenarios in which, like, you know, if you're working with a manipulator, sometimes the manipulator can treat the human arm as just like a stick to avoid, and sometimes it needs to understand that like the human has a hand and it needs to interact with the human. I think there's some cases where you do need to switch between different models. But in this particular case, we found that just being simple models and being confused works really well.
Yeah. There was a question from Vincent. Would there be a possibility to include in the safety boundary framework unexpected dynamics, for example, gliding on ice or having a drone motor suddenly stopping to work, in opposition of only considering uncertainty in the environment? Oh yeah, so like uncertainty on the dynamics versus just uncertainty on the environment.
Yeah, that's a really great question. And so we've been, that was actually kind of motivating the warm starting work, because we were saying, you know, either we can assume that, like, let's say I have some uncertainty in my dynamics and I assume that I have no idea what they are and have really intense bounds, and then I end up being even more conservative on top of this very conservative method of planning. If instead I assume I know exactly how my system works, then I could be not conservative enough. So if I like learn new information about my system dynamics, can I adaptively change what that bound would be of how it, you know, the friction coefficient or whatever it is that you're uncertain about, and be able to update my analysis very quickly. So we actually haven't tried this with Fast Track yet, of actually taking that updating stuff and putting it into the Fast Track algorithm. But I think yes, I think that it could be done. And if whoever said that is interested in doing that, I'd be happy to chat about it.
Sure. Yeah. So I guess we are sort of 10 minutes over time now, but this was like really great, pretty insightful discussions. And, particularly, I guess a lot of us loved all of the visualizations of the talk. Like there are a few comments on the chat about how nice the visualizations were.
It's the one area where MATLAB is still, I think, king is in visualizations. This is all just surf plots in MATLAB. So I also I get this a lot. So I have a set of functions for visualizing code if anybody wants my visualization tools.
Awesome.
But thank you.
So yeah, it was really fun hosting you, and we're really excited to see more work from your group, and we're also excited to see how your group grows.
Me too. Thank you so much. I had a great time, and you're all so welcoming, and I really enjoyed. These were some of the most insightful questions that I've gotten giving this talk. So it shows that you all are very bright and pay lots of attention, which I appreciate.
Sure.
Awesome.
Yeah. So
thanks so much.
Thanks so much.
Thank you. Bye-bye.